Hello, ET250. This is lecture 10. Today we're going to start our discussion on capacitors. So we're going to cover the basic equation and where it comes from. We have a Ohm's law kind of plus or minus here, I equals C dV dt. We'll talk about how it relates charge and voltage. We'll look at a fluid analogy, which is basically going to be representing as a flexible membrane. We'll look at how the capacitance is dependent on material constants and geometry, and then a common design for an electrolytic capacitor. We'll also look at some common values. We'll look at the equation on how you can compute the energy that is contained in a capacitor based on the capacitance and the voltage. And finally, we'll look at an example or the equations for parallel and series, and they're actually opposite of a resistor. Okay, why don't we begin? So a capacitor looks like this. Usually they're cylindrical. This is an electrolytic one. However, they have some square types. They have these little teeny ceramic ones. They have these really itty bitty surface mount, but they're just two terminal devices. But yeah, I think this is a very common look for a capacitor, these kind of cylindrical form factors, right? And what is a capacitor? It's an element that can store electrical charge, right? That Q. And there's a lot of uses for it. Smoothing, so if you have a signal that's bumpy and noisy, if you put a capacitor in parallel, you can smooth it out. It can be used for power factor correction, which I think you might have heard of in your other classes, but we will definitely talk about power factor correction in later lectures. It can, of course, store energy. If you can store charge, it can store energy. And it can be used to release energy very quickly. So very, very useful devices. The construction is super simple. It's just two parallel plates, and it's separated by some kind of insulating layer, a dielectric, all right? And here's an example system. Let's say we have some voltage here, and you can imagine the positive terminal is going to allow the top plate to build up positive charge, and the negative terminal is going to build up negative charge. And this is like our little ice cream sandwich of a capacitor, right? You have conducting plate, and an insulator in between, all right? And so the relationship between the amount of charge that builds up is proportional to the voltage by this equation, and the rate at which it's proportional to is the capacitance. Okay, and we use this alpha here to denote proportional, but you could also rewrite it as this equation. Okay. And so this is remember our distinction between physical quantities and units. Well, we have the four things. The capacitance C, we use the symbol C, nice and easy to remember. However, the unit is a farad, and we use the symbol F, right? So don't confuse everything. Make sure these are units of this F is not for force. This is for the unit for a capacitor, right? Okay, and now to get the equation that we are going to use is to take a derivative of this form. So Q equals CV. Well, if I take the derivative of this, assuming the C is constant, the capacitance is constant, we can take the time derivative and we get dV dt. And what's the derivative of current or derivative of charge? It is current. So we get dQ dt is I, C dV dt. So I equals C dV dt. And this is the form we will use primarily when describing a capacitor, all right? And so let's look at the form again, but a little bit more closely in the context of how we will use it to analyze circuits. I equals plus or minus C dV dt. And here's your symbol for a capacitor. It's just two parallel plates. Now, like I said before, don't confuse the symbol with a voltage supply, because sometimes you'll have a voltage supply, it'll have a longer line here. And you got to be careful when you look at an electrical diagram, and you got to make sure you're understanding the context. But in this case, you'll see for our class, a capacitor has two parallel plates. So how do you tell the positive and negative versions? Same thing as Ohm's law and power. You just look at the arrow and the voltage polarity, right? You must have both to determine the sign. Okay, so this is going into the positive terminal before it enters the element, positive. This is leaving the positive terminal, negative, okay? So that passive sign convention still holds. Now, another thing to think about is how does it behave? Like, what does this equation mean? And can we use a fluid analogy to help us give us intuition on the behavior? So what I like to think of the capacitor as is a elastic membrane, like a spring. So imagine you have a pipe with high pressure on one side, low pressure on the other side. So if you were to apply high pressure here, the spring would deflect, okay? So it would deflect in here. And if you were to get it to deflect and you were to cap off everything and then release this cap, can you imagine that all the contents would spill out? So that's kind of the idea of how a capacitor can store the charge in like the spring and then release it quickly, okay? Let's think about how does this equation relate to our intuition? Well, it's saying a dV/dt will actually give you a current. So you can imagine if let's say we were at a neutral point, equal pressures on both sides. In just the time frame where I apply the high pressure, you're having a small time of voltage change, a dV/dt, right? But once this equalizes out, once the spring deflects enough, and now you have your pressure is no longer changing. Remember, pressure and voltage are synonymous in this fluid analogy. And so once this pressure, I don't want to say equalizes, but becomes steady state, now this dV/dt goes back to zero, and then the current shuts off, right? So you get this small little blip in current, right? Just as you're filling up, and then it goes away. So I hope that helps lock in what this equation means in terms of our physical intuition, all right? All right. Now, of course, the electrical is different. You're building up charge and then can release charge, but this is our hydro analogy. Okay. So let's do an example where we can just see how this equation operates numerically, right? And so let's say we had a capacitor here. We know that it's 6 microfarads. So micro is 10 to the minus 6. And let's say there's no voltage across it. So we have 0 volts, all right? So this is the initial voltage. And let's say somehow we were able to force this step function like current. So somehow we were able to make the current go positive and negative. And the question might be, well, what would the voltage have to be looking like to get that current to go positive and negative, right? So how could we plot that external voltage, right? It wouldn't be just some steady state static voltage. It would have to change, all right? So if we have I here, and we want to find V, and we have our equation, I equals C dV/dt, okay? Then if we want to solve for this V, look how it's on the derivative side. We would have to take the integral, right? dV/dt integration equals the integral of this 1 over C ddt, right? So let's also make sure, did we get the positive version right? Because I see there's a positive essentially here. I is going in the positive terminal. Okay, we're all right with that. Okay, so if we look at this integration, right, basically we can say the V at some final time, right? So imagine we have some time here. We have, let's say, some initial time and some final time. And the final time could be any point along here. We could integrate this and get a value for that voltage at any time we choose. So imagine T0 is some fixed number, and then we integrate, remember, the area under the curve, and we get some final voltage, right? Now we have to, of course, have this initial condition, right? Because the V final time minus the V initial equals this integration. I just brought the V initial to the other side, all right? So let's think about what this means. If you can maybe correlate to what do you call it? Velocity. Let's just do this real quick. Let's say we have velocity versus time, like literally a little block, right? And we have velocity of the block. And remember, the relationship between velocity and, let's say, position is also a integral, right? So let's say you had velocity doing this, right? Velocity doing this. Okay. So that means, like, let's say you're in a car and somehow magically you're able to go up to like 10 miles an hour and then go negative 10 miles an hour, right? If you go 10 miles an hour for an hour, I would assume you've gone 10 miles, right? And so if you were to plot your position, right, I would assume you went like this in terms of your position. And then if you went negative 10 miles an hour, you'd probably do something like that, right? So if this was your velocity, this is what your position would be. Okay, so you'd have probably some positive slope and then some negative slope. And from a calculus perspective, that should make sense. If I have a constant velocity, well, how does velocity relate to its integral? It is the slope, right? So, and you can see here, this line has a constant slope, right? This has a constant slope but negative. So we have a positive slope and we have a negative slope, right? And so what does that mean for this one? So even before we do the math, if we see an I that is this, if this is I, we should see a voltage that looks like this. Okay, so I hope you can intuitively get a sense for what the answer is going to look like even before we crunch all the calculus. So I always, like I said, I want you to make sure you have the physical intuition first before you have, before we even do the math. So that when we do the math and we get a number, it's like, yeah, okay, I buy it, right? Because otherwise, if we just do the math without the physical intuition, then it's in somewhat pointless and maybe even more confusing. Okay, so we hope to expect this plot. Let's, again, even before we do the math, let's try to think of it from this membrane. In order to get current that's flowing this way, right, what's going to happen? Well, we got to be increasing the pressure on this side, right? Because once we stop increasing the pressure, once that pressure flatlines, the current's going to shut off, right? Okay, and then what we can do is start decreasing the pressure on this side, and then this thing can come back, right? So we can increase the pressure like a pump, and then decrease the pressure so that the pressure comes back. And what will happen is, as it's decreasing the pressure, the current's going to go this way, and then this is going to start losing its deflection until you're back to no voltage and equal pressure on both sides. So I hope that even before we do the math, like the intuition makes sense, the plots that we're going to see make sense, and then, okay, so now let's crunch and see if we can use our equation and do the low-level calculus, kind of just turn the crank and see if we get the same answer. All right, so we have, let's say the initial voltage is 0, so we're starting at 0 here, and now we can use this equation, right? So this is just the integral form. Let's make sure I did it right. Bring the C over, bring the dt over. Okay, that's good. And then v of tf might, and then I bring the minus v of 0 over to the other side. Great. Okay, so this is kind of what we can do. We see, for this problem, we see some nice intervals, I would say. We have a nice 0 to 2 millisecond interval, and we have a nice 2 to 4 millisecond interval, right? And the reason why it's nice is because it's a constant 6 milliamps here and a constant negative 6 milliamps here. So that's just part of the, what's given to us in this problem, right? So let's look at just this window, 0 to 2 milliseconds, because instead of trying to write an equation for this step, why don't we just write an equation for that? That's easy and integrate that. That's a much easier integration than trying to find the equation for this and then integrate that. So if we do that, we can again use this equation. So I have it rewritten. And now we can start plugging in the numbers. So this is a constant 6. Yep. This is the 6 microfarads. Don't confuse it with the 6 milliamps. And our initial voltage at this time we're assuming as 0. Now that's going to change when we do the integral for the window from 2 to 4. Okay, so if I look at this, it's not that bad. I can take the 6 out. It's a constant. So if I integrate just dt, what do I get? I get t. And then I got to integrate it from t0 to tf, right? The integration of just dt is t. And so I get 6 times 10 to the minus 3 and 6 times 10 to the minus 6. And then remember in calculus, when we integrate, we got to do tf minus t0. Okay, the plus 0 went away over there. This is nice. That becomes just 10 to the 3, right? The 6's cancel. 10 to the minus 3 over 10 to the minus 6 becomes 10 to the positive 3. tf minus t0. Well, in this case, tf is any time in between here, and t0 is 0 in this case. Okay? All right, so what does that mean? V of any time in here is equal to 10 to the 3 times tf. Okay? If we take tf at 2 milliseconds, we're all the way at 2 times 10 to the 3, right? Okay. But what we see is, as predicted, a nice line increasing up here, right? This is like a y equals mx plus b line where the b is 0. No problem. And if we take 2 milliseconds times 10 to the 3, we have 2 volts. So what this says is, this voltage starts at 0 and linearly increases to 2 volts in order to make this current be a perfect step function, right? So what I'm hoping is when we do this integral again from this thing, we should see a downward slope. So let's see if that's the case. So fortunately, this is following our intuition. Okay, so let's put this over here. Okay, so again, we're going to write down this equation. So this is valid. However, some of the minutia changes. For example, this current is now no longer the 6 because now we're integrating this window. It is negative 6 milliamps. What else? The initial voltage is no longer 0 volts, right? We didn't start at 0 volts. Now the initial voltage is the final voltage from the previous integration, and that should be 2 volts now, okay? 2 volts. Okay, what about the initial time? The initial time is no longer 0 because now we're starting over here. So now the initial time is 2 milliseconds. And the final time is any time in between 2 to 4. We can calculate different points if we just punch in different numbers, but we can just, this is like a free floating variable if we want to find out voltages in between this interval of time. Okay, so now we plug in the numbers. This is the same, -6 to T0 to TF. Again, easy integration. -6/6 milliamps over microfarads. Again, you just have a dT, TF over T0. Yep, good. You have to keep the 2 now. And then we plug in the TF minus T0. And then for T0, like I said before, it's 2 milliseconds. It's not 0. Good. And this is this equation, right? This 10 to the 3 times 2, negative becomes +2, right? And the 10 to the 3 and the milliseconds kind of cancel out. And I get a +2 plus 2, I get 4, good. And then I get this -10 to the 3 TF. So again, it's a y equals mx plus b equation where the y-intercept is 4, okay? And look at the slope. The slope is going down. That's good. That's kind of matching this behavior, right? And so what do you see? You see a linearly decreasing line starting at 4, right? And intersecting all the way down to here, right? At 4 milliseconds, can you see that we get 0? If I put a 4 milliseconds in here, I get 10 to the 3 times 4 milliseconds. I get just -4. -4 and 4 cancel out. Boom, that's here. So that I get this line. Now remember, this equation is we only care about it from 2 to 4 milliseconds. So this is the window that we care about. That's good. So if we overlay this window here with just this window here, we get this nice shape as we predicted. Okay, so hopefully this makes sense. Okay, and I have that redrawn here, right? If the current is going positive and negative, the voltage that needed to do that was a linearly increasing voltage, and then it decreased back to 0 again. Increase that pressure and then decrease that pressure. Good. And then this was our equation. So, okay, so I hope this this kind of shows you the physical intuition and how we can use actually the math to also confirm our intuitive understanding. All right, cool, let's move on. So let's look at how the parameters of the capacitance depend on your geometry and the materials. So this is the equation, much like the R equals rho L over A, this is C equals epsilon A over D. And so here's a picture. This A is the cross-sectional area of one of the plates. Remember, these are 2 conductive plates. This epsilon here is what we call the dielectric constant, and this is the material property of the insulator. And D is the distance between the 2 plates, okay? Now, the units of A are meters squared, the units of D are M, and the units of this are farad. Therefore, the dielectric constant has to be farads per meter, right? And the dielectric constant of just a vacuum is just going to be this very small number, 8.85 times 10 to the minus 12 farads per meter. And sometimes we refer to this E as ER times E0. That way we can represent this ER as a relative. So for example, ER is 1, then you're just always comparing it to the vacuum value, right? So that means the overall epsilon would just be the vacuum, right? If ER is 2, then it's just 2 times this number, if that makes sense, right? Of course, you could just give the absolute value, no problem. But it's kind of like, what is it, G's, right? 3 G's is like 3 times the acceleration of gravity. You have it relative to something so that maybe it's a little more intuitive, okay? All right, so what is this saying? This is saying that you're going to get more capacitance if you choose a material with a larger dielectric, if you choose a bigger cross-sectional area, but also if you choose a very, very thin distance. So if you can somehow get those plates super close together, the thinner the distance, you can amplify your capacitance, right? You can get more charge. Remember, more charge for the same voltage, right? Q equals CV. More charge for the same voltage if you can get those plates closer and closer together. Okay, good. All right, so how do they get these large capacitors? Well, here's an example of a cylindrical design that is a very common shape. And what they do is they have these like almost two layers of foil and then a very thin like paper-like insulator in between, right? And so it's just an electrolyte, so here's a cross-sectional area. So you have foil here, an electrolyte, and then an oxide layer, right? So just that oxide layer, kind of like that rust almost on one of the edges of the foil, is acting as the insulator. So very thin distance between the two spots. And then you have a paper insulator between the next plate over here. Okay, so why does this create a very large capacitance? Well, this whole thing wrapped around is going to give you a large area. This thin distance is going to give you a small distance, which is inversely proportional to capacitance. And the choice of material, well, this oxide layer has hopefully a high epsilon so that you can get high capacitance. Okay. So what are some examples of common values? Well, funny enough, the absolute number of a farad might be actually very small. It's hard to get big numbers. If you see like 1 farad, 2 farads, that's a crazy amount of capacitance, right? And so even these large capacitors, they might be large in terms of size and volume, and they might be able to actually contain a lot of charge, but they will seem small in terms of their farad value, like 0.02 farads. And that, I think if I go back to that initial image, yeah, here we go. So this initial image, like you see this big, crazy capacitor, this is what it's saying, 24,000 microfarads. What is micro? Micro is 10 to the minus 6, right? So this is like 0.02, yeah, 0.02. So you can see that even though they're physically large, and this capacitor might be like yay big, it might have a small number in terms of the farads, okay? What else? Little small breadboard size, you might be in the micro or the pico, 10 to the minus 12, 10 to the minus 6. And so, yeah, 71,000, 0.07, yep. Another thing to note, if you see these electrolytic capacitors, they will have a polarity. Unlike a resistor, where it kind of doesn't matter how you hook it up, there's electrolytic, these kind of cylindrical type, that you want to make sure it's in forward bias or you can damage it. You can damage this oxide layer. All right. And so forward bias means that you want the positive terminal to be at a higher voltage than the negative terminal. Okay. So yes, you can still use it in filtering, but you don't necessarily want to use these in potentially AC applications, right? They have specially designed capacitors for AC. All right. So just be aware of the application that you're intending, and they definitely have specific capacitor ratings for that application, voltage, current, all that good stuff. Okay. Let's look at the energy. How do you store energy in a capacitor? And well, look at this. Energy equals CV squared over 2. And hopefully that form looks familiar, because if you look at the kinetic energy of, like, let's say you have a mass moving, right? I like to go to these mechanical kind of analogies. They're a little bit more intuitive. 1/2 mv squared, right? So this is v velocity. This is velocity over here. Look at this. Notice the same form. CV squared over 2, mv squared over 2. Oh, nice. Okay. And so what does that mean? That means the more voltage across it, the more energy it's containing. So, and it's square. So you really got to pay attention to that voltage. So if you double the voltage, you quadruple the energy, because you get 2 to the square, which is 4. Kind of crazy dependence on that voltage. So be very careful. Capacitors are dangerous. They're just super, super dangerous. And while we're talking about dangerous, if you have a capacitor here and you have these 2 terminals, right? Don't touch these terminals, ladies and gentlemen. They're just you just don't know if there's charge on there. There could be a dangerous amount of charge built up. And if you short yourself across this, especially across your heart, that's death waiting to happen, right? Or a very painful experience. Now, some capacitors will actually come with a resistor, a very large resistor there. So this is large. And so what that means is this resistor is always bleeding off any differential in voltage and charge on here, right? However, it's large so that during normal operation, it doesn't just, short out, right? But that means if you have a machine or a piece of equipment that has now turned off, this extra charge, this extra voltage will have a chance to bleed off. Now, it's not immediately safe, and you shouldn't assume that it's safe, but this is something to think about. And there's some kind of decaying time constant, which we'll talk about for the voltage and time of this capacitor with this resistor in play, okay? So just a note of safety. Okay, so can we prove that this guy is this equation? Well, yeah, why not? Let's do it. Let's do it, right? If you want to skip forward, you can skip forward. But for those who are curious, I think it's instructive, right? Okay, so what is energy and what is power? Well, energy and power. Energy is the integral of power, or power is the derivative of energy, right? Okay, so we know the power equation, but can we take the integral of it to get the energy? Right? Well, let's look at this. Power equals IV, and that works for any element. Let's assume positive in this case because I have the current going to the positive terminal. So if I know the current and voltage, I know the power. If I integrate that power over time, then I would know the energy. And so just like before, energy of time final equals minus the energy initial, which I just put on this side, equals this integration, right? And so let's assume that we started out with zero energy, zero voltage on this guy. And then we wanted to figure out, well, what is the energy at a certain final voltage, okay? So we can take our new capacitor equation, we're using positive in this case, and we can plug it in here. So we get energy equals, instead of I, C dV dt times V of t dt. Okay, notice the dt's cancel. And I've kind of done like a sneaky change of variable here, right? So I have V of t dV. Well, instead of doing a T0 and TF, those have to change as well. So I have to go V of T0, V of TF, all right? Because otherwise the integral wouldn't make sense because I've lost my dt here, okay? So I'm going to integrate over voltage at time zero and voltage at time final instead of time zero and time final. Okay, not too bad. What did we say the initial voltage is? The initial voltage, let's say, is 0, okay? But now look what we do if we do this integral. C V dV, if we assume the capacitance constant, we can pull it out of the integration. The integral of V is V squared over 2. That's where that 2 comes in, and that's where the square comes in, right? Okay, no problem here. Now we can just plug in our values. And if we assume that the initial voltage is 0, uncharged, we get this, and we get our equation in joules, not watts, right? Okay, so you can always check the units. Does a joule equal a farad times a volt squared, right? Does it equal a farad times a volt squared? It's always good to check these kind of things. Well, we can use our new equation, I equals C dV dt. A farad is an amp second per volt. Good, amp second per volt. If I put an amp second per volt in there, amp second per volt, look at one of the volts canceled here, and I get an amp volt second. Well, what's an amp volt? Amp volt is power, which is a joule per second, but a second and seconds cancel. Yes, joules per joules is a match. I am satisfied. Very good. You do the same thing with this one, right? You could say, this is also joules. Remember, energy is the universal currency, right? Does this match? What do we have? Kilograms. I haven't done this, so maybe I should. Meters per second squared. Is that right? This is velocity. What do we have? Kilogram meter squared over second squared. Okay. What do we know about a joule? A joule is a Newton meter. Is that right? Okay. And what's a Newton? Is a kilogram meter per second squared. Is that right? Okay. Oh, we're kind of having a kilogram meter per second squared times meter. Oh, look at that. That's a Newton meter. Oh, that's a joule. Yes, victory. Okay. So we can see that even this equation in kilograms and meters per second squared is also a joule. Nice little unit check just to make sure everything is up to par, right? Okay. Let's do an example. So what do we have here? Let's say we have a capacitor, and of course, because we're talking about capacitors, and they give us a capacitance 10 microfarads, and they tell us that the plot of energy per time is shown like so. So it started out at 700 joules, it dropped down to 200, and then actually dropped down to negative 300. So the zero line is like, you know, over here, right? Maybe I should have drawn it like with the zero line there. But anyways, look at this. This is decreasing. So what does that mean? If the energy in this is decreasing, that means this guy is delivering power. So if we were to calculate the power in here, we should compute a negative number if we're calculating from the perspective of power absorbed, right? So the slope of this line is the power. And so what's the question here? Find the voltage and current at 5 seconds, right? Find the voltage and current at 5 seconds. So we have a V and we have I, okay? And what else do they say? At t equals 5 seconds, the energy is 200 volts and is decreasing by 500 joules per second. So this is the power actually, right? Okay, so let's assume, we got to make an assumption. Let's say assume that this V is positive, okay? Well, if the V is positive, and if this is decreasing power, the sign of I better be negative, right? Okay, because this is probably delivering power, right? The energy in here is decreasing. So let's see if we can use our equations to figure some of this out, right? So first thing here, let's just use our equation to solve for the voltage, right? So energy equals 1/2 CV squared, okay? So we can say at 5 seconds, we got 200. We have the capacitance we were given, good. The voltage, we can do this, plus or minus square root, right? We have the plus or minus, but we're making an assumption that we have a positive voltage. So that's just, so in this crazy capacitor, it has 6,000 volts, 6,324.56 volts, okay? Now, the power, like we said, because we know that it's decreasing, should be negative 500 joules per second. We know that our power absorbed equals positive IV from here, okay? But it's also equal to negative 500, okay? Let me repeat that so you're not confused. From the physical behavior, what do we have? This is negative 500. From the equation based on the reference direction and polarity, positive. We made an assumption that the V is positive, so we're putting a positive here, and now we can calculate the current. It's just negative 500 over 6,000. Good. We're seeing a negative number. Everything's good. So 0.079 amps, negative sign, delivering 500 joules per second. So hopefully all this stuff makes sense and is also consistent with the theory that we're learning. Okay, good. Okay, let's look at capacitors in parallel, not series, parallel. Interestingly enough, capacitors in parallel add and that's the opposite of resistors. So if we had a bunch of capacitors like so, C equivalent equals C1 plus 2 plus 3, where they're in parallel. Okay, so fix that. And so one way to prove it is you could use our new Ohm's law version of a capacitor, I equals C dV dt, right? Notice how current is going to the positive terminal here. So we have positive, okay, good. We could use KCL here at this top node. We want these two to behave equivalently. Remember, same voltage and current for the same conditions. And we want these three to be represented by this one. Okay, so I could take this individual equation, punch it in these three. By KVL, all these voltages are the same. And you can see here, I can distribute or pull out the dV dt. If I want this behavior to, this equation to behave like this one, I better have C equivalent equals C1 plus C2 plus C3. Okay, so that's how we show ourselves that capacitors in parallel add up. Now in series, they add by the reciprocal rule, 1 over 1 over kind of business, right? And to show that to ourselves, we could again compare our more complicated multiple series capacitors and our single one, right? So this, we want to see, can we get this form similar to this and get this kind of relationship? Well, here, the voltages by KVL all add up. So V1 through V3 add up to this. What else do we know? If we took the derivative of all these, we'd get this form, good. What about the current? The current's the same for all these because this is all in series, okay? And it looks like we could just punch in our individual equation, our capacitor equation, right? If I solve for dV dt, I get 1 over C, so 1 over C1, 1 over C2, 1 over C3. And if we look at what's going on, we can pull out the I, and then we get a 1/1 business, right? Just like this. So hopefully this convinces you that capacitors in series, from a theoretical point of view, what do? They add by the reciprocal. So they actually decrease in the overall capacitance, okay? What else can we note about this? Why would you use this over this, right? Why would you use this over this? Well, here you get an increase in capacitance, right? Here you get an increase in capacitance. And if let's say you're kind of load sharing all that current. So that's kind of nice. So that's a big, and typically you see that, right? You see that capacitors are put in series for this reason. Now, why would you put it in series like this? Well, at the expense of decreasing your overall capacitance, what you might gain is the ability to apply it to a capacitance to a higher voltage, right? Okay. All right, so let's keep going. So this is an example. This is kind of similar to that example with the bike pedal power meter, in that what it would be an application of this, right? And so this is what would be an application of using this capacitance, right? And so one application could be a liquid level sensor, right? So imagine you have like a gas tank, right? And so you wanted a way to check what the liquid level is, and potentially, well, not potentially, but you can see if this liquid is kind of cutting here and it's moving up and down, can you imagine that the dielectric constant, or the material in between, is changing, right? So notice if this thing was fully submerged, now the dielectric constant is depending completely on the liquid. If the liquid drops all the way down, now the dielectric constant is air, right, or vacuum, right? And it's somewhere in between. And so you can imagine that the capacitance of these two plates actually changes depending on the liquid level, right? And if you could measure that change of capacitance, potentially using similar circuits, maybe a Wheatstone bridge-like thing, then you could get a reading on how much liquid level is in this tank, okay? Well, let's look at how we can use our capacitance equation and see how that change in capacitance depends on the level of this liquid. So we can set the problem by saying, let's say the total distance of this plate is L, the width is W, and the distance here is D, and the height from 0 to the top of the liquid is X. Well, that means this is L minus X, right? And let's say that the total capacitance, if this liquid level was down to 0, is 200 picofarads. They say that the relative dielectric constant is, what do we call it? 15 for the liquid, but 1 for air. And that should make sense because it's just a vacuum. So it's the liquid has a dielectric that is 15 times greater than that of the air, okay? And so this is, remember, this is our formula. The total dielectric constant is just ER times E0. So we are asked to find C of X. C of X, right? How the capacitance changes as a function of this liquid level height. So let's bring back our capacitance equation, epsilon A over D. So this A, this D, and then the epsilon, right? Okay, that's good. And so A is just width times length. Good, width times length. Okay, good. And E0 is 8.8. So we have all the important pieces of this puzzle to find out what that equation is, right? We know that C max for the air is given, it's 200 picofarads, but they didn't give us the other one, right? Could we find it, right? So we don't know it yet, right? We don't know what C max of the liquid is, or in other words, when X equals L, but we could find it, right? So we know that ER is 1, we know ER is 15, so we know that the C max of liquid has to be 15 times greater than that of the air, right? Okay. So that should make sense because the geometric values are constant, right? So that's easy. So what else can we find? Let's see here. This is a cross-sectional view of our setup, right? And so we know that the capacitance is going to be whatever the air is times the percentage that's in air, right? Plus the percentage that's in the liquid, right? It's kind of like this balance, right? So if you are, let's let's think about it. If we are 100% air, right? That means we're 0% liquid and this goes away, right? And so we're just all of this. If we are 100% liquid and 0% air, because these two percentages kind of trade off back and forth, then we're none of this and all of this. Okay, that makes sense. And then if we're 50-50, then we're halfway in between here, right? 50% times this plus 50% times this, and we're halfway. Okay, so this seems like the form that would make sense, right? And so getting these percentages, that's pretty straightforward. Well, the percentage that's air is L minus X over L, right? Okay, L minus X over L, that's the percentage that's in air. And what about the liquid? It's just X over L. Easy. So you just punch that in, and that's our equation. Not too bad. Okay, so now we could just go and punch in all the numbers, right? So what do we have here? L, okay, that's fine. And that pulls out, okay, L minus X plus 15X, okay, no problem. We can put a 200 in here. What do we have? Yeah, crunch, crunch, crunch. So we get this equation, right? And so all this equation does is notice the L's, like if we actually knew a number, like 1 meter, they go away, they kind of bury into here. And this is a C of X equals some number, 200 picofarads times 14 times X plus a number. Again, a Y equals MX plus B, nice linear relationship. And here's a plot of that as X is 0, right? And this hopefully makes intuitive sense. If X is 0, the liquid's all the way at the bottom, we should see 200. That's the capacitance of air. As you increase the liquid rises, the capacitance increases, and then we get to all the way up here, okay? So hopefully pretty simple, straightforward example, and I hope this lecture helps solidify your understanding to capacitors. Okay, all right, see you in class.